Hey everybody, Jonathan here. In this video, I'll be giving you my take on section 11.3, which is all about the integral test for convergence. So, in a lot of situations, you have a series that's defined by a function. In other words, the nth term of the series, an, is equal to f of n for some function. If that function happens to be continuous, positive, and decreasing on the interval from 1 to infinity, then we can apply the integral test to see if the corresponding series, the sum from n equals 1 to infinity of the f of n's, is going to be convergent. And the integral test says that the improper integral from 1 to infinity of f of x dx is convergent if and only if the corresponding series is convergent. So that means when the integral is convergent, so is the series, and it means when the integral is divergent, then so is the series. I went ahead and made a GeoGebra activity to illustrate the integral test. For this activity, you can choose any function. However, what I say will only be valid if you choose a decreasing function. Right now, I've let the function that's decreasing being 1 over natural log of x plus 1, because, why not? What we can do is we can show the series summing from 1 to infinity of the f of i's. We can now interpret it as these rectangles. The idea being is that f of 1 is the height of the height up to the function at 1, f of 2 is the height up to the function at 2, and I can make a rectangle with width 1 for each of those, and therefore the area of the first rectangle is f of 1, the area of the second is f of 2, and therefore all of these rectangles that go on forever and ever, their total area equals the sum of this series. And on the same graph, I can also show you the improper integral. The improper integral from 1 to infinity is just the area under the graph. And if we look at both at the same time, this is only really apparent for the first few, because the graph gets flat really quickly. But because the function is decreasing, and we're using the left endpoint of each rectangle to be the height, then everywhere else the function is below the top of the rectangle. And that means that each rectangle is completely over the area under the graph. So all the rectangles contains the area under the graph of the function. So just from this, we've got that the improper integral from 1 to infinity is less than or equal to the series from I equals 1 to infinity of f of I. And from that we can deduce several things right away. First off, if the series converges, then the improper integral will converge because it'll be less than it. And if the improper integral diverges, then the series diverges because it has to diverge to infinity, and our series is going to be greater than something equal to infinity. And now observe there's something else I can do in this case. If I instead use the right endpoints of the series, if I use the right endpoints at each rectangle for the height, then the rectangles are all under the graph. Only now, this first one, since the height is determined by the value at 2, this area of this first rectangle is f of 2, the next one is f of 3, and so on and so on. So this is now the sum, this area of all these red rectangles is the sum from I equals 2 to infinity. And that sum, notice, is completely contained in the area under the graph because each rectangle was under the graph. So that means that the sum from I equals 2 to infinity of f of I is less than or equal to the improper integral from 1 to infinity of f of x. And from that, we can tell that if the improper integral converges, then the series has to converge. Technically, there's more proof going on here, but the partial sums will turn out to be a monotonic bounded series. And that's why the integral test is true. However, the integral test gives us something that's even more useful than telling if a series converges. It tells us how many terms of a series we have to add up to get within a certain error. In general, it is extremely difficult, if not impossible, to find the exact sum of any series that's not a geometric series. There are tricks that work on a few series, which we'll see down the road in a bit, but in general, if you just give me an arbitrary series, I'm not going to be able to find it. However, when you have a series that comes from a function that's positive, decreasing, and continuous, then if we make the observation that no matter where we start our rectangles, they're always under the graph, starting at the same point. And furthermore, we talk about the remainder term of a series. So the remainder term for a partial sum. The idea is we want to know how close is a partial sum. How close is the nth partial sum to the actual value of the series? So what we can do is take the whole series and subtract the nth partial sum. However, that just means we're starting the series at n plus 1. So that's Rn. And in here in red, we've got the sum from I equals n plus 1 to infinity. It is completely contained under the graph. You can't even, it's kind of hard to tell here, but all the red rectangles are contained under the graph, but the graph's pretty flat. So that means that our nth remainder term will be less than or equal to the integral from n to infinity of f of x dx. And this is great news because this integral is something you can find in general. And we can use that to bound the error term, and therefore we can determine, suppose you need to get within, I don't know, 1/1000th of the exact answer. You can figure out how many terms you actually need to add up for that kind of accuracy. All right, that's all for now. See you next time.